Hello everyone and welcome to this module on the introduction to continuum mechanics. So in this video we are going to introduce the cylindrical coordinate system and then derive some of the some of the basic equations for the divergence curl and the gradient of tensor field, vector field, and also the scalar field. So let's get started by the introduction to cylindrical coordinate system. So introduction. Uh, so the cylindrical coordinate system, unlike polar coordinate system, is a 3D coordinate system. So you have x, y, and according to the right-hand rule, you have z here. And you have a vector here. So we call this r, for example. And in this coordinate system, if you have, this point r here, so this is the vector r, sorry, here, and you have the point p here. This is the point. So here, to refer to this position vector, this r here, so you'll need a combination of, the position vector in this plane x y, which is essentially the polar coordinate system. So it is RER plus something in the z direction. So we have this z here. So this is the position vector. And if I want to be clear on this. So we have a situation like this, where we have, let me just extend this. So we have something like this. So as you see here, you have a projected kind of vector here on R, with a small r, on xy plane, which is like the polar coordinate system, and you have theta increasing in this direction. Therefore, if you have r increasing this direction, so this is r, and if theta is in this direction, therefore this is e theta, they are orthogonal to each other, and this is the way that ez is basically increasing. So then we have r as this one, and since we need dr for further calculations, we need to find this out also. So maybe this space here is not enough, so I move everything here. So we have dr. So we have the derivative of r, which is small r, which is dr. Then we have er plus, then we have r d er plus, we have z, it becomes dz ez plus z dez. So from the previous video on polar coordinate, we know that this der is d theta e theta. Therefore, we have dr er plus r d theta e theta. Then we have this dz plus this zdez. And as you see here, dez basically is constant, so it does not vary from this point to this point. It also has a constant value, so its derivative is definitely 0. So this is 0. So overall, this reduces to this. All right. Now with this introduction, where you saw that a position vector is characterized by this equation here. So you need a combination of polar coordinate and somehow a Cartesian coordinate to refer to a position vector in a cylindrical coordinate system. And you have the point P, you have three unit vectors, ER, E theta, and EZ. And remember this increasing direction for R and theta. We're going to ready for the gradient of a scalar field. So the gradient of scalar field. All right, so we defined del F. So let F be a scalar field. So F is a function of R, theta, and Z, remember. So we have del F here, and this del F, basically the F dr is equal to del F, the gradient of this. And df is del F dot dr, where we have this, this component of del F. So we assume that it has a component AR in ER direction, a theta plus AZ, AZ. So it has a component in E theta. It has also an unknown component in EZ dot. That we have this dr here, which is essentially this position vector. Sorry, this position vector here, the derivative of this position vector, which I copy from above. So here. So I may call this, I don't know, maybe 1 or maybe a star. So I have dr er plus r d theta e theta plus dz e z. Perfect. So what I get is ar dr plus a theta r d theta plus dz. Now I have my vector field f, r, theta, and z, and I know that df is partial derivative of f with respect to r dr plus partial derivative of f with respect to theta d theta plus partial derivative of f with respect to z dz. So if I compare 1 and this is 2, so compare 1 and 2, then you get that AR, partial derivative of f with respect to r, a theta is 1 divided by r, partial derivative of f with respect to theta, because we have an r here. So a theta r is equal to this, so a theta is 1 divided by r, partial derivative of f with respect to theta, and az is partial derivative of f with respect to z. So overall, del f is equal to partial derivative of f with respect to r e r plus 1 divided by r, partial derivative of f with respect to theta e theta plus partial derivative of f with respect to z e z. All right, so next we have the gradient of a vector field. All right, so if we have a vector like v, r, theta, and z, it is definitely a function of these three. So it has a component of dr, which is also a function of r theta and z, e r plus v theta, r theta, and z, e theta plus vz, r theta, and z, e z. All right. And the gradient, basically this dv dr is del v, therefore dv, so is del v dr. So since this is a second order tensor, so I can simply substitute this del v with t, so I can write it t dr. And remember here, I did not put this dot here because now we have a tensor times a vector field. So it is not a vector dot a vector. So the dot product is only defined for two vectors. All right, so we have dv, which is basically t dr. And here we have t, and this dr definitely is a vector. So we have a component of er, r from start again, from here, r d theta, if I'm not mistaken. Yes, plus the z e z. So this is equal to dr t er plus, r d theta t e theta plus dz t e z. Good. Then we have this t e r, and if you remember, this was d j r e j, and j here is r theta and z. Therefore, we have t r r e r plus t theta r e theta plus t z r e z. Then we have t e theta. It is t j theta e j, and again we have this j equal to r theta and z. Then tr, maybe it's better to write like this, tr theta er plus t theta theta e theta plus t z theta e z. Then we have t e z equal to t j z e j, which is equal to t r z e r plus t theta z e theta plus t z z e z. All right. So therefore, this dv is dr t r r e r plus dr d theta r e theta plus dz t z r e z plus, right, so we have r d theta t r theta er plus r d theta d theta theta e theta plus r d theta t z theta e z plus dz t r z e r plus dz t theta z e theta plus dz tz e z. So here I am simply just substituting this in the above equation, this set of equations here. So now I have this. So I sort this out based on, er, e theta, and e z. So I have dr trr plus r d theta tr theta plus dz trz er plus I have dr theta, oh sorry, d theta r plus r d theta theta plus dz d theta z e theta plus I have dr t zr plus dz t z theta dz d z z e z. All right. Now I call this one 2. So we have 3 here. Then I have v, r, theta, and z. As I already said, maybe I can just copy and paste this from here. So next we have this, right? So next we have this, and then dv is dvr, as you see here. Then we have dvr, r, theta, and z, er, but I'm not going to write this r, theta, and z, so simply write er. Plus, next we have vr, der. So as I said, it is like, having two functions, fx and gx, and you want to take the derivative of this with respect to x. So you say that dfx dx times gx plus fx dgx dx. So it is like this. So then we have dv theta e theta plus v theta d e theta plus dvz e z plus vz d e z. And here there are some things we need to take care of. This is 0 because we know that EZ does not change. We have DER, so this one here is d theta e theta, and this e theta, if you remember, it is minus d theta er. So we next substitute this. So we continue. We have dvr er plus vr d theta e. Oh, sorry, this is e theta plus dv theta e theta plus, minus v theta d theta er plus dvz e z. Perfect. So now we have this dv r component here, partial derivative of vr with respect to r dr plus partial derivative of vr with respect to theta d theta plus partial derivative of vr with respect to z dz. And then we have this dv with respect to theta. So this component is partial derivative of v theta with respect to r dr plus partial derivative of v theta with respect to theta d theta plus partial derivative of v theta with respect to z dz. Because you also know that this vr is also a function of r theta and z here. So all these components. Then we have dvz is equal to partial derivative of vz with respect to r dr plus partial derivative of vz with respect to theta d theta, and finally partial derivative of vz with respect to z dz. Perfect. So next we need to substitute this VR here, the VR, dv theta, and dvz here. So maybe it was a good idea just to remove this parenthesis here, so you don't make a mistake. Right, okay. So we need to substitute this dvr, dv theta, and dvz in the above equation here. So again, so substitute above equations in dv gives. So we have dv as, all right, so we have dvr, which is this one, okay, partial derivative of vr with respect to r dr plus partial derivative of vz with respect to vr with respect to r, then vr with respect to theta, d theta plus partial derivative respect to z d z e r plus, then we have vr d theta e theta, then we have plus this dv theta here. This is the partial derivative of v theta with respect to r dr plus partial derivative of v theta d theta plus partial derivative of v theta with respect to z d z e theta minus this term here, v theta d theta d theta e r plus this dvz here. So it is partial derivative of vz with respect to r dr plus partial derivative of vz with respect to theta d theta plus partial derivative of vz with respect to z d z e z. Perfect. Then we need to sort these all together. So I have partial derivative of vr, so I have er here and here, and this d theta, so I have to put it here. So dr plus partial derivative of vr with respect to theta minus v theta d theta plus partial derivative vr with respect to z dz, this is er, plus, all right, so I have partial derivative of v theta with respect to r dr plus partial derivative of v theta, partial derivative of theta with respect to theta, sorry, minus plus vr d theta plus partial derivative of v theta with respect to z, oh sorry, d z e theta. And then finally we have partial derivative of vz with respect to r dr, partial derivative of vz with respect to theta d theta plus partial derivative of vz with respect to z d z e z. So essentially what I did is just writing this del v here and then minus del v transpose, then the whole is multiplied by half because I want to reproduce this antisymmetric tensor of del v, and here it is. So you see that the diagonals are 0, and we can here simply calculate the uh, let's say, the dual vector of this del v. So if we recall, if you recall, this 2 ta was minus 2 t 3 e1 plus t 1 e2 plus t 2 e3. And if you have some difficulty with this, you can refer to the polar coordinate video, and because I already devised a way to remember this. So this become minus 2 of t theta z e r plus t z r e theta plus t r theta e z. So here I simply substitute 1, 2, and 3 with r theta and z. All right, so we have minus 2. So this 2 actually goes with, it cancels out with this 2 here. So I only write minus here. So partial derivative of v theta with respect to z minus 1 divided by r partial derivative of v z theta is here e r plus partial derivative of v z r v z with respect to z. This is e theta plus 1 divided by, oops, I can write it here, 1 divided by r partial derivative of v r with respect to theta minus v theta minus partial derivative of v theta to r e z. Perfect. So if I just rewrite everything, so this 1 divided by r partial derivative of v z with respect to theta minus partial derivative of v theta with respect to z e r plus partial derivative of er with respect to z minus partial derivative with respect to r e theta plus partial derivative of e theta with respect to r minus 1 divided by r partial derivative of er with respect to theta minus v theta e z. Of course. All right. All right. All right, so the next topic is the divergence of a tensor field. Divergence T. Oh, sorry. Tensor field. And if you recall, for this, the book used the definition and expression here, said that the divergence of T, that's A, is the divergence of T. We put a dot here because you know that the divergence actually integrates the order. So we have a vector dot vector. So we have the divergence of T transpose A minus the trace of del A T transpose here for every vector A here. So so we have different components for divergence of T. We have divergence of T with respect to R. Then we have the divergence of T with respect to theta. Then we have the divergence of T with respect to Z. Because the divergence is the tensor is second order tensor, so the divergence actually degrades its order, so it becomes a vector. So we expect to have a vector here for the divergence of T. So let us first start with A equal to ER here. So we have the divergence of T, the R component. So it is equal to the divergence of T transpose ER minus the trace of del ER T transpose. So we first start with this expression and we find its divergence. Then when we move on to the next term, we start with this del ER, we find del ER T transpose, and finally we find the trace of the second term. So we have T ER here, and we knew that it was T J R E J, where J was R, theta, and Z. So based on this, we had T R R E R plus T theta R E theta plus T Z R E Z. So here we have T transpose ER, as you see. So this become the transpose of this. So it becomes RR. So this is RJEJ. RR ER plus R theta E theta plus T R Z E Z. And as you see here, this is a vector. This is VR, this is V theta, and this is VZ. So from the equation 234.6 of the book, we can calculate the divergence of T transpose ER based on VR, V theta, and VZ, partial derivative of TR with respect to R plus 1 divided by R, partial derivative of TR theta with respect to theta plus TRR plus partial derivative of RZ with respect to Z. Good. Then for the next term, we have ER as 1 ER plus 0 E theta plus 0 E Z. This is VR, this is V theta, and this is VZ here. So based on the equation 234.5, so we have del ER T transpose. So maybe I this bit down. All right, so this is equal to 0, 0, 0. So if you substitute, these V theta, VZ, and VR in equation 234.5, you get this, tensor here, 0, and all the rest are 0. Then we have T transpose, so this is TRR, and now we have TR theta here, and then TRZ here, theta R here, theta theta, and theta Z, TZR, TZ theta, and TZZ. So we have 0 here, 0 here, and 0 here. And then we have 1 divided by R, T, R theta, ER. We have 1 divided by R here, T theta, theta, ER. 1 divided by R, T, C theta, ER. And the rest are 0. So the trace here del ER trace T. Oh, maybe. I guess that I forgot this. That's here. Sorry, this here. It's here. So I have this here. So it is 1 divided by RT theta ER. Perfect. So now the divergence of T, the R component, is partial derivative of TR with respect to R plus 1 divided by R partial derivative of T R theta partial derivative of theta plus T R plus partial derivative of RZ with respect to Z minus 1 divided by RT theta theta. Now we move on to next one, which is the divergence of now we have, sorry, A as E theta. So the divergence of T theta component is the divergence of T transpose E theta minus the trace of del E theta. Sorry, this adds T transpose. All right. Then again, we have here T theta, T E theta, which is Tj theta, Ej. This is T R theta, ER plus T theta theta, E theta plus T Z theta, E Z. So T transpose E theta is T theta J E J. And here, if you have, this is TR, T theta R, sorry, ER plus T theta theta E theta plus T theta Z E Z. This is VR, this is V theta, this is VZ. Perfect. So from equation 234(6), I have the divergence of T transpose E theta. So I have VR, V theta, and VZ, so I plug it into this equation where we also got in here. So partial derivative of T theta R respect to R plus 1 divided by R partial derivative of T theta theta partial derivative with respect to theta plus T theta R plus partial derivative of T Z with respect to Z. So next I have E theta, which I can write as 0 ER plus 1 E theta plus 0 EZ. This is VR, this is V theta, and this is, oh sorry, this is EZ, and this is VZ. Perfect. So if I plug in into equation 234 and 5 for del E theta here, and then I find if I plug into this equation 234(5), so I find the gradient, so I multiply by T transpose is 0 0 0 1 divided by R minus E theta. I have all the components here 0 0, and these are all 0. Then I have my let's say copy and paste it here. Perfect. So all right, so this becomes minus 1 divided by tr theta by, sorry, tr theta e theta minus 1 divided by r t theta e theta minus 1 divided rt is e theta e theta 0 0 0 0 0 and 0. So the trace of del er t transpose is this minus 1 divided by rt theta e theta. So the divergence of t here, the theta component, is partial derivative of t r plus 1 divided by r, partial derivative of theta with respect to theta plus t theta r plus partial derivative of theta z respect to z plus 1 divided by rt r theta. That's it. So finally we get to the divergence of, so a is equal to ez, so the divergence of t, the z component, is the divergence of t transpose e z minus trace of del e z t transpose. All right, so I have t ez t jz ej, so it is trz plus t theta z e theta plus t z z e z. I just write this one here so to just have a better understanding of what we are doing here. So the t transpose is nothing but t z j e j. You see here that the subscripts are swapped. So I have t z r e r plus t z theta e theta plus t z z e z here. And this is VR, this is V theta, and this is V Z here. So you know that if we plug this into equation 234 6, then you get the divergence of t transpose er as a partial derivative of t zr with respect to r plus 1 divided by r partial derivative of t z theta respect to theta plus t zr plus partial derivative of t zz with respect to z. And then I have this easy here, so I can write it as 0 er plus 0 e theta plus 1 e z here. And this equation here is this equation 234 and 5 gives the gradient of ez. So if I multiply it by t transpose here, so I'm gonna have 0 0 0 0 0 0 all 0. Then I have t transpose, which this becomes 0. And it is a tensor, of course. So the component of divergence of t in the z direction is a partial derivative of the zr with respect to r plus 1 divided by r partial derivative of the zr respect to theta plus the zr plus partial derivative of tzz with respect to z. And it's very good to follow these steps one by one. So you also have the idea of how to proceed further in, for example, in a third order tensor, the divergence of a third order tensor. So you know that you have basically a second order tensor, and you have to find all the components one by one. So now we move to the Laplacian of a scalar field. So we have del to f, if you remember. So we have del to f here. So if you recall, we had this del f here, which was the partial derivative of f with respect to r, er plus 1 divided by r partial derivative of f with respect to theta, e theta plus partial derivative of f with respect to z, e z, which was essentially a vector, because we said that the Laplacian, because we said that the gradient increases the order of your field. Whether it is a scalar field, it becomes a vector field, or a vector field becomes a second order tensor. So del 2f is nothing but del dot del f. So I have the divergence of the del f, which is essentially, so here we have VR, this is V theta, and this is VZ. If I just shift this down a bit. Yes. All right. So I have the partial derivative of the VR component, then 1 divided by R of, and I also have this, this is a vector, right? This is a vector. And we already calculated this in the divergence of a vector field here. So 1 divided by r divided by 1 partial derivative of v theta here. So plus partial derivative of r, yes, and plus partial derivative of the vz with respect to z. So if I do this, so I have second partial derivative of f with respect to r twice plus, and here I have, so r is not a function of theta, so I can treat this as a constant, so just bring it out. 1 divided by r squared, second partial derivative of f with respect to theta, plus 1 divided by r, second partial derivative of f with respect to r twice, because now I have, sorry, so this is partial derivative of f with respect to r, plus second partial derivative of f with respect to z. So next we have the Laplacian of a vector field, which is the last part here. So the Laplacian of v, of a vector field. So again here, the book used the definition of del 2v, so del 2v is equal to del divergence of v minus curl of curl v. And if you see again here, you have a divergence, so it is a scalar field, and you have the gradient of a scalar field, which is a vector. You have the curl operator, which is a vector, applied on a vector, so it is a vector. So again, it applies on a vector, so we have a vector minus a vector. So finally, we expect to get something like a vector here. So del v, del 2v has an r, theta, and z component. So we start by here the the divergence of v for the component del 2v r. All right, so we have the divergence of v and the partial derivative of vr with respect to r plus 1 divided by r. This is something we already achieved, plus partial derivative of vz with respect to z. Then we take the gradient of this, so del this divergence v, which is this expression here. So I have to copy and paste this here. So maybe it is a good idea just to copy, then paste this in here, and then here, and then here. So I have, this is ER, sorry, this is ER. This is plus 1 divided by r, partial derivative of this with respect to theta, e theta, and this is plus partial derivative of this with respect to z. So finally, we have second partial derivative of vr with respect to r minus 1 divided by r squared v theta where vr plus 1 divided by r. So I guess that it might be a good idea to take this derivative. So I save some time and you can check with me finally. So this is the final equation here. So for the del of the divergence of v, so basically I applied all these operators here on expressions here. And now we move to del dot v. So we already calculated this, so we can rewrite it here. 1 vz theta minus v theta with respect to z er plus vr vz minus minus 1 divided by r vr with respect to theta e z. So here again we have this as vr, this is vz, and this whole expression here is v theta, and this is vz, this whole expression here. So maybe it's a good idea just to write it like this. Okay, so this is vr, v theta, and vz. So again, we need to rewrite everything in the form of del v. So we treat this again as a vector and we rewrite everything. So I pause the video and you can check with me later. So now I have plugged in all the equations here and I took the derivatives. So I have ER, E theta, and EZ components. So now I calculated this term here, del curl of curl V. And here I have the gradient of the del V. So I subtract this del divergence of V from this curl of curl V. So I will have three, let's say, expressions for del 2V. So del 2V R, and maybe it wasn't a good idea just to put this in here, because next I'm going to just drive all them explicitly. All right, so I have this this one from here. I need to copy this and also expand it and subtract this. Subtract this from here. So maybe it is a good idea to say that this is 5. All right, this is 5 and this is 6. So 5 minus 6 gives, so we have del 2V R is equal to, so I pause and write everything. So I have this gradient of del V here, and I have curl of curl V here. And finally, I remove the, the terms that cancels out each other, and finally I got this for the R component. And now I move to del 2V theta component. So now I have again the expression, this first line for the gradient of the divergence, and I subtract the curl of the curl V here. And finally, I got the equation for the theta component of the gradient of the Laplacian of the vector. So now I move to del 2V, the z component. Now I have the z component of del 2V. Here I have the gradient of the divergence term, and here I have the curl of the curl V, and I have the final expression here. And this actually recaps the basic tensor algebra in or operations in, let's say, the cylindrical coordinate system. We also have, for example, the curl of the tensor field and something like this for, for second order tensor, for the third order tensor, and they're a bit difficult and a bit tricky to deal with. So I tried to upload some solved problems on my GitHub page. So at the end of this chapter, you will have a series of solved problems where you can actually solve and check your answers with mine.